We'd like to welcome you to another in a series of webinars designed for departments of transportation. I'm Terry Bills, and I'm the Transportation Industry Manager here at Esri. And today I have the great pleasure to be joined by Paul Durdin of Abley Consultants. And Abley is one of our business partners based in New Zealand. Today's webinar is focused on an issue of critical importance to DOTs, namely roadway safety, and looking at ways in which we can address the quite significant issue of traffic fatalities and serious injuries on our roadways. Traffic safety is, for almost every DOT that I know, one of their top priorities. And yet, for the last several years, we've actually seen an increase in the number of fatalities and serious injuries on our nation's roads. And as a result, this is an issue of strong importance to all of us, and especially here at Esri. Before we begin, I'd like to point out that we're recording this webinar, and while everyone will be on mute, there will be time for question and answers at the end of the presentation. You can type your questions into the question box. We'll try to answer as many as time allows. Additionally, these slides, which are part of this webinar, will be available to you on the GeoNet group, Departments of Transportation. And we'll give you the link to that at the end of the webinar. So let me start off by putting the U.S. into a bit of a comparative context. The countries of Europe have for some time been strongly committed to a EU-wide program of road safety. As part of their commitment to the UN Decade of Action, as well as their own Vision Zero initiatives, a number of countries have been able to make quite significant reductions in road fatalities, to the point to where Europe now has the world's safest roadways. In a recent 5-year period, Norway was able to reduce road fatalities by 43%, Greece by 36%, Spain and Portugal by 32%. At the same time, in the early 1970s, the US used to have the world's safest roads, but has since fallen to 30th in road safety, measured by fatalities per 100,000 people. And as you can see, in the 1990s, Slovenia actually had a fatality rate 5 times higher than the US. Now, through their efforts, they're roughly twice as safe as the US. So we start with the recognition that road safety is really a function of political will, and some countries have been able to make significant improvements in very short periods of time. And had we followed the European trajectory in road safety over the last 20 years, we would have saved roughly 20,000 lives a year, according to a recent study. In the past, the focus of safety management programs was always on changing driver behavior and on driver education programs. But in the late 1990s, independently, both Sweden and the Netherlands began to take a different approach. The Vision Zero approach was developed and officially adopted in Sweden in 1997, and the Sustainable Safety Program became the dominant approach in the Netherlands in the same year. And both started from an ethical position that human safety should be the top priority and that traffic deaths are preventable. They both recognize that humans make mistakes, and as a result, we should focus on better highway design and ultimately making our roadways more forgivable to human failure. And while each approach took a holistic approach to road safety, each represented a fundamental shift from the prior safety paradigms. These major initiatives that take from these concepts include the UN Decade of Action, which is worldwide, Vision Zero, which, as we said, originated in Sweden, but now has been adopted by a number of US cities and state DOTs, and the US DOT itself has initiated the Road to Zero initiative, which started in 2016. Many of these same concepts underlie the work that we'll see today from Abley. And key tenets of the Vision Zero approach include, as we've said, that traffic deaths are preventable, and perhaps most importantly for our purposes here, that we should adopt a data-driven approach to improving traffic safety. And that's precisely where I think GIS can make a significant contribution. Key strengths of GIS for safety management include the areas of data collection, data integration and data management, data analysis and decision support, and finally, effective communication and public involvement. And how do we involve the public in our safety initiatives? So it's my hope that this will be the first of a number of safety-focused webinars that we'll offer, and because this represents some of the most important work that we do in the DOT and in GIS. So with that, I'm going to turn the presentation over to Paul Durdin. And Paul, I'll let you take it over and introduce the work that you've been doing on out-of-context curves.
Thank you, Terry, and welcome everyone to this webinar. So Terry's provided a terrific introduction to road safety and the change in thinking that has happened over the past decade in particular, and the momentum that the safe system approach has gathered globally. So today, the presentation is going to focus on the use of GIS technology, and in particular, a focus on horizontal curve safety. Now, I'd just like to start today just with to put this into context, the scale of issue that's currently faced in the United States. And one way of thinking about that is, before this webinar ends, it's likely that 4 people will lose their lives on America's roads, and one of those 4 is likely to lose their life through a roadway departure crash on a rural road. That puts the challenge that the industry faces into context today. It's a large issue, and not just one that's faced in the United States. It's also present in New Zealand, Australia, and globally. As an industry, we understand how to warn motorists of the presence of horizontal curves through the use of signs and markings, how to alert them if their attention is lacking through interventions such as rumble strips or speed-activated warning signs, how to reduce their likelihood of crashing in the event of poor approach speed or misjudgment, such as high-friction surfacing, and how to protect road users in the event that they fail to negotiate a curve safely through roadside hazard removal or side barriers. So why then, if we understand how to treat horizontal curve safety, do we have such a problem? Well, one of those reasons is that crash patterns in rural networks tend to be dispersed, especially in low volume rural networks. And because of this, a crash clustering approach can be unreliable to predict where the next fatal or serious injury crash may occur. The majority of horizontal curve assessment methods are manual, which means that they are very time intensive and can rarely be applied at a network level, simply because there are thousands upon millions of curves in any given network. This is supported by NCHRP Report 500, a guide to reduce the lead. And part of the introduction there that I'd like to draw your attention to, it does say that there are typically no formal means of reviewing all horizontal curves and identifying those with adverse safety performance. The absence of a network level screening tool to assess the safety of all horizontal curves across a network leads practitioners to work from assumptions that may be erroneous. Some of these assumptions include that crashes are indicative of underlying safety risk. Well, we know that this is not true, particularly in low volume networks. That the locations investigated are the least safe parts of the network. Well, how can that be known without a network assessment? And that interventions can only be justified at locations with an established safety issue. But we still have crashes that keep happening, and the United States, as well as many other parts of the developed world, are experiencing an upward trend in roadway fatalities over the last 2 to 3 years as economic conditions have reinvigorated. So there is a large challenge before us. These assumptions typically occur in the risk identification stage of the overall life cycle of a typical road safety program. So what happens if the assumptions around risk phase are wrong? I like this very simplistic chart here, which shows that the importance of making correct assumptions at the start of the process gives you the greatest opportunity to influence a positive outcome. The further down the track you get, the least influence you have. Plus also the cost of rectifying the assumptions increases as you get down the track. So getting the assumptions right at the risk identification phase is critically important. So let me tell you a little bit about the evolution of that horizontal curve risk assessment tool that we've developed here in New Zealand. So New Zealand's road safety strategy for the current decade is called Safer Journeys. It adopts the safe system approach to road safety and has a vision of a safe road system increasingly free of death and serious injury. As part of Safer Journeys, it identifies signature projects, which are exemplar projects that adopt a complete safe system approach to road safety. Signature projects provide a platform for trialling innovative approaches and treatments across the 4 safe system pillars. The Eastern Bay of Plenty region of New Zealand was identified as an area where a signature project could make a demonstrable advance in reducing road trauma for all road users. The New Zealand Transport Agency commissioned a multifaceted signature project in this region. One of the work streams involved the development of a methodology that would allow road safety risk to be better understood at a network level, especially at horizontal curves, which was the location of 58% of all injury crashes in the region. An objective of the signature project was to develop a risk prediction model that allowed horizontal curve risks to be understood at a network level, preferably without the need for any manual data collection. The challenge put to us by the New Zealand Transport Agency asked us to reconsider the traditional ways of thinking about safety on road networks. It essentially asked us if we could understand road safety risk at a network level, provide data-driven, evidence-based analytics to support policy and investment decision-making, move away from a reactive to a proactive approach to assess road safety, identify a technique that targets high-risk locations, take existing data that is held by road authorities and other agencies and add value to it, and to avoid the need for expensive and time-intensive data collection or field assessment. So after an extensive literature review, the process selected as being the suitable basis of the project was the Austroads operating speed model. The operating speed model sets out a procedure for calculating speeds along road sections based on the geometric features of the road and typical behaviours of drivers on higher speed roads. The model was based on 3 primary elements: the driver, the road, and the vehicle. It is developed on the premise that driver behaviour approaching, traversing, and exiting a curve is a function of the preceding geometry, the approach speed, curve radii, and length of straight immediately following a curve. This information can then be used to identify the design limits for curves, which can be a proxy for curve risk when considered in conjunction with approach speed. The operating speed model is intended to be applied in a manual manner along manageable lengths of road corridors. Essentially, this involves a road agency identifying a corridor of interest and then following the model's segmentation and assessment process to classify horizontal curves along the length. For road agencies, manually implementing this model across all roads in a network would be both time-consuming and cost-prohibitive. However, as the inputs to the speed model are spatial in nature, an opportunity was identified to automate the model so so it could be applied at the network level in a timely and cost-effective manner. Abley adapted the model using geospatial workflows, including ArcGIS models and Python scripts, to model vehicle speeds along rural roads to assess the safety risk of horizontal curves at a network level. The input data required for the assessment is a high-quality centerline that accurately reflects the geometry of the road, speed limit information, and a digital elevation or terrain model. Curve identification involves segmentation of the road centerline into 10-metre lengths and calculation of the radius for each 10-metre section over 13 metres using a chord height and length formula. Road corridors are then segmented into discrete sections defined by horizontal geometry and demarcated by the start and end points of straights, isolated curves, or a series of closely spaced curves with similar radii. Maximum desired speeds for each segment are calculated as a function of the speed limit, terrain, and curvature of the road. This figure shows that as terrain and geometry becomes straighter and flatter, speeds are higher compared to mountainous and tortuous alignments where speeds are lower. Next, operating speeds are calculated along the road centerline in both directions. Operating speeds are calculated by running a Python script that sequentially evaluates each element of the road, curve or straight, to model vehicle speeds and driver behaviour. In simplistic terms, motorists are modelled to accelerate when straights are longer than 200 metres, to maintain speed where straights between curves are less than 200 metres long, and to decelerate where the approach speed is higher than the operating speed range for a curve or series of curves. Curves are then classified based on the relationship between modelled curve approach speed, horizontal curve radius, and modelled curve departure speed. Curves are classified as being unacceptable or undesirable, and these are referred to as out-of-context curves, or within limit or desirable, and these are referred to as within context curves. On the right, you can see that the curve analysis is carried out bidirectionally, so that curves may have different curve contexts in one direction compared to another. Results show that curve-related crashes, such as roadway departure and head-on curves, are significantly overrepresented on the out-of-context curves compared with curves that are within context. This chart shows that on the New Zealand road network, approximately 75% of it is classified as straight, with the other quarter being distributed amongst the 4 curve classifications. However, more than 50% of curve-related crashes occur on the unacceptable and undesirable parts of the network. This technique has been extended to the New South Wales and Queensland states of Australia, and now we've assessed more than 70,000 miles of roadway of state and local government roads, and we find a similar relationship holds true in all of these areas, although regional variations are noticeable. At a network level, injury crash rates on out-of-context curves are 450% higher than straights and nearly 100% more than curves that are within context. The disparity is especially pronounced at unacceptable out-of-context curves. This demonstrates that out-of-context curves are locations of heightened risk per road user compared to curves that are within context and significantly heightened risk compared to straight sections of road. This slide is intended to show the influence of curve negotiation speed and curve context. Analysis of injury crash rates by curve negotiation speed and curve risk classification show that crash rate is most disparate between out-of-context curves and within context curves at lower negotiation speeds. Take, for instance, a curve negotiation speed of 65 kilometres an hour. So that's equivalent to 40 miles per hour. Typically, a curve improvement project would seek to reduce crashes by in the order of 30%. So if the curve is picked independently of curve classification, this line shows a indicative 30% reduction. If the curve is out of context, the chart shows that we could have confidence of getting nearly a 10% increase or greater savings than if it was done independently of curve classification, and significantly lower likelihood of reduction potential if the improvement project was delivered to a within context curve. So the key point here is that curve classification is really critical for generating higher levels of improvement. More than 3 times the level of improvement is likely to be achieved for delivering an improvement project to an out of context curve compared to a within context curve. So you may be asking, is there an inherent risk at horizontal curves that cannot be reduced by engineering interventions? The answer is no. And a good way of demonstrating this is to look at the crash rate of that as a function of functional classification of roads. The dotted lines show the national average for curve-related crashes and all crashes in New Zealand. And we can see that the highest classification of roads, the national strategic and regional strategic roads, have crash rates that are below the national average for out-of-context curves. However, as the category functional classification lowers, we find that the crash rate extends above the national average. And this is not surprising, as more resources are thrown at the highest order roads to create safer environments, whereas roads functional classification reduces, so too does the level of resource allocated to reduce road trauma. This figure here tries to illustrate that point. In the top left corner, we can see a regional strategic road. It has chevrons, sealed shoulders and barrier on the curve, progressing to an arterial rural road, which still retains chevron markers on curves. However, we have a narrower shoulder, but the roadside hazards are quite a long way back from the road. As the roadway reduces in status to a primary collector, we find that the delineation tends to reduce, and we have roadside hazards entering into the clear zone. And on secondary collector, we often lose edge marking lines, and in this instance we can see a utility pole placed on the inside of a curve, which would prove to be a very severe hazard if a vehicle departed the roadway in that location. The horizontal curve analyses are being used by road controlling authorities in New Zealand and Australia for a number of reasons, and I will touch on these later. But in simplistic terms, they're being used to prioritise corridors for mass action highway improvement programs, to evaluate the benefit of speed management interventions, and to provide an evidential basis for funding applications. I'll now take you to one of the web viewers that we have developed for Transport for New South Wales. That should be on your screen now. So New South Wales is a very large state in Australia, and it contains 42,000 kilometres or 26,000 miles of state-controlled rural roads. This screen here shows the first stage of the modelling process, which is the calculation of operating speeds at a segment level. And you can see here that as alignment becomes more tortuous, operating speeds reduce, such as in this area, as alignment is higher, is straighter, we have higher operating speeds. If I then take you to a specific example, when we run the curve analysis, we see here that in the ascending direction, so from south to north, we have different curve classifications along the corridor. So the red and yellow are our out of context curves, and the blue and green are the within context curves. And this varies by direction. If you look at these curves at the top here, you will see that the first curve encountered from north to south is out of context because it follows the end of a straightish section of road where operating speeds are higher. But in the other direction, it is within context because the user has just traveled through a tight curve, meaning their approach speed into that next tight curve is within context of that curve. So how does this curve analysis correlate with crashes on the network? I can bring those up. Just waiting for those to load. Right, that should be there now. We can see that curve crashes tend to be very closely correlated with the curves of greatest risk. So even as we pan out and see what might appear to be an innocuous curve at the southern end of this section, there have been loss of control crashes there. And it doesn't mean that there won't be crashes on the within context curves. It's simply that the crash rate on the out of context curves are a very heightened area of risk. So if I return to a couple of the specific examples of how the analysis has since been taken further, one of those is a corridor-based analysis technique, which has an objective to prioritise corridors for mass action curve investigation and improvement programs and to improve route consistency for road users. One way of doing that is to create additional metrics that prioritises curves. We've developed two metrics. One is an out-of-context curve risk and the other is an overall curve risk. The out-of-context curve risk measures the number of injury crashes occurring on out-of-context curves per out-of-context curve along the corridor. It's developed as a proxy for the number of crashes that can be targeted if out-of-context curves along the corridor are improved to an appropriate standard. The other metric, overall curve risk, measures the number of injury crashes occurring on all curves normalised for traffic volume. This is designed to filter out corridors that have a high number of crashes relative to the number of curves, but a low crash rate per vehicle traversing the corridor. Low crash rates indicate that safety improvements may not yield as much safety benefit when compared to corridors with higher crash rates. A simple risk matrix is developed so that highest risk corridors are identified only from those corridors that have high risk ratings under both metrics. Now, for each jurisdiction, we work with the road controlling authority to set thresholds and identify suitable target lengths of network to fall into each of these categories. So for the Centre for Road Safety at the Transport for New South Wales, they wanted around 10% of their network to fall into the high risk band, with progressively higher proportions of network falling into each of the subsequent lower risk bands. And this can be adjusted depending on the appetite, budget and level of investment that the road controlling authority may want to deliver. So for New South Wales, 10% of the network that was analysed represents around 2,600 miles of network. And as you can see, the calculated percentages align very closely with the target lengths. So what do these results look like? Well, when we start to analyse the results at a crash rate level, at a corridor level, we can see that the highest risk corridors have a crash rate that is 2.5 times that of the second highest risk category. And this is a really critical finding because it means that efforts can be targeted to risk, thus optimising investment and saving lives if we focus on these highest risk corridors. If I return to the web viewer, we can bring up the curve risk ratings underneath. Bear with me as I zoom out. And we can see how the risk levels look at a corridor level across the network. So the intention here is that for the Centre for Road Safety Transport for New South Wales, they will be focusing their high-speed horizontal curve investigation and improvement programs on the corridors that are high risk, coloured black, and then progress on to the red corridors and potentially the orange coloured medium risk corridors. And that way they'll know that they're addressing corridors where the crash risk per horizontal curve and along that corridor really has an opportunity to deliver those demonstrable benefits to road safety. Another of the applications that is being used is speed management. And an objective here is to set speed limits that are safe and appropriate for the function, use and risk of each road. And the metric used here is the Nielsen's power model. So Nielsen's power model says that changes in speed are directly correlated to safety outcomes. And there is a formula where it says estimated DSI, and DSI stands for death and serious injuries, is a function of the current estimated DSI multiplied by a speed change ratio to the power of an exponent. So what we did is we modelled different speed limit scenarios across the network, and then we're able to assess the relative benefits that could be yielded on a corridor by corridor basis if speed limits were changed. On average, we found that a reduction in speed limit from 100 kilometres per hour, so 60 miles per hour, to 80 kilometres per hour, that's 50 miles per hour, will yield approximately a 27% reduction in deaths and serious injuries. So having access to this information helps road agencies demonstrate that a speed limit reduction has the potential to deliver road safety benefits. The operating speed model allows these agencies to set and test different speed limit scenarios, therefore helping them understand the potential impact on road safety outcomes as well as travel times and operating speeds. And they can assess the impact of different speed limits on the number of out-of-context curves along each corridor. So if we select a corridor, we can see here that this road, which has Castlereagh Road, has a current existing speed limit of 100 kilometres an hour and an existing operating speed of 97 kilometres an hour along the corridor length. So it's geometrically constrained such that people are not, on average, reaching the posted speed limit over the entire length. The crash numbers are shown in this pop-up box, as well as the number of unacceptable, undesirable, and desirable curves. If we click through to an 80 kilometre an hour scenario, we can see here that the estimated FSI, so New South Wales uses an FSI, fatal and serious injury acronym, would yield a 32% reduction, and it would reduce the number of unacceptable curves along the corridor by 6, so there would be 0 left, and the number of undesirable curves would reduce by 2 down to 4. Now, the reason why speed management is able to remove out of context curves from the corridor is that it takes away the top end speed, and thus the relationship between approach speed to a curve and safe curve negotiation speed falls within a safe limit. So what are the key messages that I'd like to reiterate today? Well, one of those is that this bridges a gap between an awareness of a major safety issue, that is crashes at horizontal curves, and detailed strategies to reduce the likelihood and consequence of crashes. It really provides a technique to ensure that the risk identification stage is done at a network level. The process uses existing data. It does not require any data collection or field assessment. So it is available to all road controlling authorities. The risk assessment approach is independent of historic crash data, which makes it proactive and a better method, particularly on low volume networks, to understand risk and predict where the next high severity crash is likely to happen. This then means that investment can be optimized, and it provides an evidential basis for targeted road safety investment. And ultimately, what we all want to achieve is to save more lives. So targeting improvements at out of context curves and on high risk horizontal curve corridors will save more lives than improvements delivered independent of curve classification. You can find out more about this work and some of the other proactive risk techniques that we've developed for the New Zealand Transport Agency and others via these links that are shown here. A copy of the presentation will be provided to you after the conclusion of the webinar. Our work has been well received in New Zealand and Australia and in the United States. Here are some of our team receiving awards. One of those in the middle was at the ATSIP Traffic Records Forum in New Orleans in August, where we were very proud and humbled to receive the Best Data Visualization Award for our work, where we're combining GIS analytical techniques with our domain knowledge of road safety to present road safety information to professionals across the globe. Thank you very much for your time today, and I'll hand the presentation back to Terry.
Okay, thanks, Paul. I appreciate that. And let me reiterate actually not only the slides, but this entire presentation will be available after the webinar. So if there's any of your colleagues that actually were not able to attend, they'd still like to listen to the webinar, it will be posted on our website. And again, all of these links, both not only Paul's, but these other links will be made available on the GeoNet website. So feel free to type any questions into the question bar, and we'll answer as many as we can. There's a number so far, so let me start off. I guess the question really, and you may have mentioned this, but really what information do you need? What are the data requirements to conduct this analysis? If you could just maybe speak a little bit more to that, Paul.
Sure. So the analysis is requires a high quality road centre line. So a road centre line that is geometrically accurate, that reflects as closely as possible the actual geometry of the road. That's critical so that we can carry out the segmentation and the operating speed analyses. We also require the speed limit information and a digital terrain model. Now, all
Okay, the question is, how did you calculate the estimated operating speed, or how do you calculate the operating speed?
Okay, good question. The Austroads operating speed model sets out maximum desired speeds that vary as a function of the speed limit, the horizontal alignment, and the terrain at a corridor level. And then each segment has an operating speed range attached to it, and we apply acceleration and deceleration formulae for each of those segments that will model vehicles increasing speed, maintaining speed, or decelerating speed, depending on the nature of the horizontal alignment for that segment.
Okay, let's see. And I guess another question, do you have an automatic method to define your horizontal curves, PC, PT, and radius, or do you use the information from the original design of the existing road inventory?
We have an automated methodology for doing that, where we segment the network, the centre line, into 10-metre sections, and then we calculate the radii using a formula that is based on a rolling 30-metre average across that. We've done many calibration tests against other approaches and find that our method is equally compatible as other methods, including field measurement, which is really encouraging, so that it means our methodology can be applied with confidence across a road network that has a high-quality centre line.
Okay, and is there a tool that's made available to construct your model, is another question.
To date, we don't have that. That's our intention in the long term. At the moment, this work is being delivered in a professional services capacity, but that's where we'd like to get to in the future.
Okay, and I guess there's a question, again, if you could just define how an out-of-context curve is defined.
Okay, so an out-of-context curve is defined based on the chart that was shown in the presentation. Now, what this means is if the approach speed along a straight section or a tangent section heading into a curve exceeds a certain threshold relative to the curve radii, then the curve will be classified as out of context. Basically, this means a driver needs to decelerate beyond a determined threshold, which means they must modify their behaviour significantly in order to safely negotiate the curve. A within context curve may have the same negotiation speed, but if the approach speed is lower, it's deemed to be within context because the amount of speed modification is deemed within limit.
Okay, and obviously for both New Zealand and Australia, what was the source of your digital terrain model?
That is a good question. For New Zealand, that was made available to us by the New Zealand Transport Agency, and I personally don't have the information available. I could ask one of my colleagues and have that made available to participants. In Australia, we purchased a digital terrain model and simply overlaid that over the centre line, and that was more than adequate.
Okay, here's another one that's going to test your knowledge of geometry. Do you consider the spiral curve or only consider the curve as a simple curve?
That's a good question. The analysis technique will identify any a horizontal curve as having a radii that is less than 500 metres, so approximately less than 1,500 feet. And because this is calculated every 10 metres along a segment, it is possible that you could have compound curves. So you may have a curve followed by a partial straight and another subsequent curve. we do apply techniques that follow to do a smoothing process. The spiral nature of curves isn't specifically identified within the curve process at the moment. However, that's something that is an opportunity for further development in the future.
Yeah, and I think the next question really sort of follows along. It said, do you confront the curves, radii, and parameters with the real ones, i.e. do you do that comparison? And do you consider vertical profiles too and their interactions?
Okay, so the way that this process was initially calibrated was based on the Eastern Bay of Plenty project, and the New Zealand State Highway has access to very high quality data that's collected by high-speed vehicle technology, and we were able to apply the simplified methodology that we have, and we achieved over a 97% matching rate for curve radii calculation, which gave us a lot of confidence and gave the New Zealand Transport Agency confidence that simplified methodology could be applied at the network level beyond the state road networks onto networks that had less information available to them. What was the second part of that question, Terry?
And do you consider vertical profiles too and their interactions? So I think that's you've answered that, but if you want to.
We don't consider a vertical profile on a curve-by-curve basis, but it is taken into account in the overall terrain and the maximum desirable speed at a corridor level.
Okay. There's another question. Can this be applied to smaller non-state network analyses?
Look, that's a great question, and yes, that's absolutely one of the key benefits of this analysis, is that it's available outside of typical state network. So the analysis in New Zealand has been applied to all sealed rural roads with a speed limit in excess of 70 kilometres per hour, and simply that's achieved through having speed limit information and a geometrically accurate road centre line.
Okay, and another one, I guess just maybe you've answered, but how has this methodology been used in practice? And maybe you could speak a little bit to that.
Yeah, okay, so in October this year, New Zealand had a change in government, and the newly elected government has a very much increased focus on road safety and wants to reduce the upward trend in safety that we've been experiencing over the last 2 years. And as part of that, this analysis that we completed last year is now being used to identify corridors where the New Zealand Transport Agency and local government can go and deliver a suite of what they're calling quick wins to the network. So that is where they can get out there and improve safety at horizontal curves through techniques that are very easy to implement, generally low cost. So signs, markings, high friction surfacing, some shoulder widening, maybe some roadside hazard removal. So that's now within a program. The government's announced an increase in funding to support that initiative. In Australia, in New South Wales, the analysis has been used by the Centre for Road Safety as part of a package to support a $500 million increase in road safety funding of the rural roads over the next 10 years. So look, that's particularly pleasing on our part, that our analysis is forming that evidential basis to highlight the need for investment in these rural road networks, which have traditionally suffered from an underinvestment over many years, which is reflected in the high crash rates that occur on horizontal curves.
Okay, and I'm going to exercise the prerogative of the moderator and ask my own question. Paul, can you speak? Obviously, you do more than just out of context curves analysis with GIS. Could you just sort of briefly speak to some of the other types of analyses that you've actually applied in New Zealand and Australia?
Okay, so I sit on the KiwiRAP technical committee. So KiwiRAP is the equivalent of US RAP in the States. It's part of the International Road Assessment Program protocol. And through that technical committee, we've been asked to develop a series of assessment techniques that can be applied at a state and local government level. So we look at high-risk intersections. That's identifying intersections where the likelihood of death or serious injury is particularly high relative to other intersections that have similar features. We've also worked with the New Zealand Transport Agency and the industry at large to develop a technique which is known as infrastructure risk rating. So this is similar to the RAP star rating process, but it's based around the principle of utilising existing data sets that are typically held by road controlling authorities or other government agencies to predict the underlying risk of roads. This is both at an urban and rural level along corridors, independent of their crash history. And we've calibrated that process and applied it in both New Zealand and Australia, and we find that the relationship between the infrastructure risk rating scores and personal risk, which is your injury crash rate, is particularly very strongly correlated. So that's absolutely terrific, and that's helping guide investments into areas where there have not really been many crashes, but we can have confidence that they are high risk, and in the future they're likely to be areas where fatal or serious crashes will occur.
Yeah, and you actually applied that methodology actually to Utah, did you not? And do a comparison between the U.S. RAP calculations and your own IRR calculations?
That's right. So as part of our work, we wanted to understand how well these techniques are transferable beyond New Zealand and Australia. So working alongside Utah, who made available access to a lot of their data, we applied the IRR model, the infrastructure risk rating model, to 800 miles of the Utah network. And without modifying or calibrating any of the IRR variables to United States conditions, we had a very strong correlation. And upon comparing that with the star rating process, we found that IRR was even a slightly stronger predictor of personal risk or injury crash rate than star rating. So that was especially encouraging. We did the same on the 800 miles with the out of context curve analyses as well, and again identified very similar results for single vehicle roadway departure crashes on curves in terms of those crash rates by curve classification. So that all points towards the fact that a curve is a curve in New Zealand or in the States. If it's unsafe, it's unsafe, and that's reflected in crash history. Okay,
good. Well, maybe we can get you to come back at a future date to talk about that work as well. Last chance for any other questions. If not, we'll go ahead and we'll conclude this webinar. Again, I want to thank all of you for being on the line today. I want to especially thank our guest, Paul Durdin from Abley Consulting. And again, I'll reiterate that these slides as well as the this webinar will be available after, and we'll actually have it posted as soon as we can, and the slides will be on the GeoNet website, GeoNet Departments of Transportation website. So with that, again, thank you all, and we'll close this webinar. Thank you.